What we're going to do then is say, all right, polynomials were a good start. And remember what I was just saying about if it's a big degree polynomial, it shoots off to infinity faster. So somehow when we ramp things back, that first example with the quadratic, things looked good. So somehow if we could say, let's keep it to a low degree. Well, how do we keep it to a low degree if I have lots of data points? Well, what we can do is, someone else's suggestion, we can go piecewise. So let me show you what that would look like. If we take piecewise linear segments as a hypothesis, well, that looks good in this particular case. It's much better than the polynomial was. If I could actually draw them right, that'd be better. So it's continuous. Even that looks smoother and more sane than what we got out of the polynomial. Now, of course, we just lost something there as well. We lost the smoothness because these are straight lines that run into each other at an angle. So we've lost the smoothness by doing this, but it gives us an idea. Instead of trying to fit through all the data points with one master function, one master 7th degree polynomial, why don't we think about fitting little bits of the function together and then just tie them, smooth out the edges as they transition from one to the next. So we're going to do little blocks of functions, but we're going to ask that they transition nicely between each other. And it turns out that's not too bad to do. What we're going to do here is use something called a spline. So we're going to run it and then take a look at the output and see what we think of it. All right. This is all the same kind of stuff. Run it. All right. So this is what's called a spline interpolant. Notice it has a little bend to it, but nothing like the bend that we saw in the polynomial. And certainly in the lower end, it's much more smooth, or it's about the same thing, has the right shape. This is something we could imagine sketching by hand and being pretty happy with it. Okay? So just to compare the structure in the code, it is almost identical in structure to what we just did. Before we had our x and y's, and again, think of functions as someone or something in a kiosk that we give some data to. Here's my x and y, and I'd like you to fit it to degree 7. Please give me back the polynomial. When we look at the spline, we're going to give it the x and y's, and that's it. So here are my data points. Please, can you do some interpolating for me? It gives us back something that, again, modeled on the help function in MATLAB, is called PP. So it's a piecewise polynomial. The first one was a polynomial. PP is for a piecewise polynomial. And then we go back and say, all right, to another kiosk, hey, I found this piecewise polynomial on the ground. Actually, Spline gave it to me. And I gave it a bunch of x coordinates that are linearly spaced from 0 to 20. I would like you to build me the graph that describes this piecewise polynomial. And those will be y values. And so what we get is exactly in parallel to the fit, get a polynomial, then evaluate the polynomial at some x's to get y's. It's fit a spline, then evaluate the spline at these x's to get the y values for the spline. And we just plot the x's against the y's. And again, it gives us that graph there. So the structure is the same conceptually. It's a little more complicated under the hood. We'll talk about that. But conceptually, it's the same thing. Fit, and then use the fit with some x's to get a graph. All right. Questions or comments about anything in the code there beyond the whole new spline function thing? Yeah, go ahead.
What does the hold all and hold off function do again?
Right, the hold all and hold off, if I plot, where's my first plot? There's a plot up here. If I do a plot command, usually it clears the screen. If I want to hold the data and the other thing on the same plot, in between them I need a hold all to say, okay, plot the dots, then hold on, I'm not done yet, plot this other thing, and it'll appear on top of the dots. Excellent. And depending which version you have, apparently the new version, hold all and hold on do the same thing. For the older versions, hold on cycles the colors, hold all cycles the colors by default, and hold on keeps everything blue, unless you specify a color. Yeah?
What's the warning you're getting?
What's the warning I'm getting? Excellent. So this is our polynomial. So if you look at the crazy polynomial we had a second ago, whoops, not that polynomial. Let's try that again. What's happening here is that you're actually solving a system of equations. to get the coefficients. And it turns out that it's hard to find exactly the right polynomial to go through. There's some actual variation that would give you basically the same fit, and that's what it's complaining about. So badly conditioned means there's a lot of 8th degree polynomials that'll look a lot, 7th degree, that'll look a lot like this, and the linear solver is having a hard time narrowing it down exactly. Which is another hint that probably a polynomial fit to a lot of data is not the way to go. But in this case, it's a linear solving error that's coming out, or warning. It's actually fine, but it's just warning you something might be off. Actually, sorry, let me take one more step back, just because I have to say it because I'm compelled. No, most of you probably won't care. If you think of the 20 number here and you do x to the power 20, 20 is the number. 20 to the power 7. We're doing 7th degree polynomials. 20 to the power 7 is a huge number. So you'll notice that it gives us a hint here. Try centering and scaling as described in Help Polyfit. If you massage your data so the numbers are smaller, like 1 to 2 or something like that, then 1 to 2 to the power 7, that's fine, like it's 10, 20. And what happens when you're solving these linear systems is, if you have super, super big numbers, like 20 to the power 7, and super small numbers, like 0 to the power 7, the fact that you have that range actually causes some problems with linear solvers, because you're trying to subtract big numbers from small numbers, and that often leads to round-off errors in the computer. So that's another thing that's pointing out. Should have mentioned that earlier. OK, so splines. Let's talk about splines, seeing as they seem to be a nice alternative in principle to this polynomial wiggle that we're getting. So what are they? Splines by default are cubics. Okay? And why are cubics a nice thing? Well, we drew linear segments, and they were fine, but they were only continuous. It turns out if you want continuous derivatives, well, that means you need a quadratic. And if you want continuous second derivatives, which is what makes curves actually look smooth, then you need cubics. So it's just an extension. And you can build quadratic splines. You can build 4th degree splines. But for these reasons here, the most natural looking curves are the cubics, because they're the simplest that have the nice properties that we're usually looking for. So they tend to be the balance between complexity and niceness that we have here. So looking at the math briefly, I'm not going to make you solve any of these equations. But the idea is that we are going to build cubic functions. So it's going to be some number times x cubed plus some number times x squared plus some number times x plus a constant. That's a cubic. And we're going to define one of those on each interval. So we're going to have our data points, and we're going to build one cubic here, another cubic here, and a third cubic here, each one with its full A, B, C, and D values. Now, we don't want to just do that randomly. We want to have it behave itself nicely, and what we mean by that is, on the intervals, a cubic will look fine. Cubics are smooth, so between here and here, things are going to look pretty. What we're worried about is, as we go from one pretty region and then join to the next region, that things are going to go off the rails. It's going to look weird. So we just insist that, hey, when I come from this side, the blue line and the green line have to match up. So the two polynomials have to agree with each other. OK. That seems like a pretty reasonable thing to say. I would also like, notice the primes here, the derivatives to match up. So as I go from here to here, I would like the slopes to be the same at the point when we cross. And that's what makes it not a cusp. It makes it look a little smoother. And last but not least, we would like the curvature to be the same as we come in from both sides. And that's, again, it's a visual thing. It's not as obvious as a cusp, but it makes things look smooth. And I believe, yeah. Here's kind of what might happen if we didn't have each of those properties. So we've got our data, and this would be just continuous, but the primes are not equal. Pi plus 1. So I might have a nice smooth curve, but then it doesn't join. It joins at a cusp to the next thing, and that's not so nice. But if I smooth that out and I actually enforce that the derivatives are the same coming from this way and from that way, and this way and that way, this looks smoother. You do notice some, maybe it's a little hard to see, it's a very subtle effect, but there actually are some things that don't look quite right. The derivative is actually right, but it still looks like it's kind of jumping somehow as we go from the red to the green. That's where the most obvious one is here. And that's the second derivative smoothing this thing. So if we actually require one more step, which is that the second derivative be the same on both sides, then we get something that looks really, really nice over here. It's made up of 1, 2, 3, 4, 5 different cubic functions, but they're chosen, the coefficients are carefully chosen so that when you join them together, it looks seamless. That's what a spline is. All right? So a seamless looking, try to write that a little more legibly. Seamless looking joints or transitions between the cubics. So they are 5 different functions here, but they're picked so that you can barely see by eye. If I didn't color those, you wouldn't know where the transitions were.